Hello again, welcome to another lesson in geometry. Today we are covering section 10-8, geometric probability, and this is our last section in chapter 10. All right, so we have some review, right, true or false. A point indicates a location and has no size. This is definitely true. It's one of the first things we learned this year. A line contains a finite number of points. This is also true. So use a diagram at the right, circle the segment that includes point S. So PR is this blue one here, so that's no good. Doesn't have S in it. PT goes from here to here. Oh, that definitely has S in it, so we can circle it. And segment QR, just to make sure, did not include S, so we can get rid of that. Vocabulary builder, probability, related term, geometric probability. The definition of probability is an event in the likelihood that the event will occur. So the probability of event is a likelihood that an event will occur. Our main idea in geometric probability, the favorable outcomes and possible outcomes are geometric measures such as lengths or segments or areas of regions. So remember our theoretical probability, the probability of an event is the number of favorable outcomes divided by the number of possible outcomes. Okay. All right, so underline the correct words to complete each sentence. The probability of an event is the ratio of the number of favorable outcomes divided by the number of possible outcomes. Okay? So remember, this is our theoretical probability. So in real life, if we do the experiment or the event enough times, we will get close to the theoretical probability. But if we only do it a few times, we could be way off. Okay? So if there are 7 red marbles and 3 green marbles in a bag, 1 marble is chosen at random. Write down the theoretical probability that this marble will be green. So we're looking for the probability of a green. So the chance of a green would be 3 that we want out of a total of 10. Be careful, it's not the stuff we want out of the stuff we don't want. It's the stuff we want out of the total things we want. Okay? So as a fraction, this would be 3 out of 10. As a decimal, this would be 0.3, and as a percentage, this would be 30%. Okay, so we would suspect that if we did this experiment enough times, that about 30% of the time we would get a green marble. Okay, on page 2 here we have probability and length or area. Okay, so we're going to use length and area measurements to calculate some probabilities. Okay, so first off, probability and length. So point S on AD is chosen at random. So here is segment AD, and we're going to put point S some random place on it. The probability that S is on BC, that red part of the segment, is the ratio of the length of BC to the length of AD. So the red part is the part we want it to land on, okay? And then that's the total place where it could land on. All right, so let's complete a couple more examples like this. What's the probability of S being on AC? Okay, so that would be the length of AC divided by the length of the whole segment, which is AD. And what's the probability of S being on AB? That's the length of AB divided by the length of the whole segment, which was AD. All right, so probability and area here. So point S is chosen at random in region R. So region R is the whole gray thing, and I'm going to throw S on it somewhere. Close my eyes and hit it. Okay, so the probability of S is in region N is the ratio of the area of N divided by the area of R. Okay, so find the probability of the given areas if the region R is 11 and N is 3. So the area of the whole thing is 11, and the area of this part is 3. Okay. So what's the probability that S will be in N? Well, N is 3, and the whole thing is 11, so 3/11. Okay, let's get some practice in on this. So using segments to find probability, point H on ST is selected at random. So this is ST. And I'm going to put H somewhere on that. Okay. What is the probability that H lies on SR? So we want to know what's the probability that when I plop H somewhere between S and T, it ends up somewhere between S and R. So first off, find the length of each segment. So the length of SR is the absolute value of 2 minus 8, which is going to give us 6. And the length of ST is the absolute value of 2 minus 14, which is going to give us 12. So the probability of H being on SR would be the length of SR divided by the length of ST, the whole thing, which would be 6 over 12 for 1/2. Okay. All right, so the probability that H is on SR is 1/2, or if we want to write it as a percentage, 50%, and you could also write it as a decimal as 0.5. Problem number 2, using segments to find probability. A commuter train runs every 25 minutes. If a commuter arrives at the station at a random time, what is the probability that the commuter will have to wait no more than 5 minutes for the train? Okay, so this is going to spread over 2 pages here. First, we're going to circle the time in minutes before the train arrives that the commuter will need to arrive in order to wait no more than 5 minutes. So the commuter needs to get there. The train will have to come in the first 5 minutes that the commuter is waiting. So somewhere between 0 and 5. Okay? Circle the diagram that models this situation. So which diagram represents the wait of 0 to 5? Okay? So this is the commuter waiting for 5 minutes. Okay? Complete the following for number 14. What is the length of the favorable segment? This is 5. What is the length of the whole segment? This one's going to be 25. So why did they make that whole segment be 25? Let's flip back and read that question a little more closely. It said the train runs every 25 minutes. So we know this is the part that the commuter is waiting, and a train should come sometime in this whole thing of 25. Okay? All right, so what's the probability that the commuter will have to wait no more than 5 minutes? Well, the chance the train comes in the first 5 minutes is 5, that length of this segment, the red part, divided by the whole segment, which is 25, which will make the chances of them not having to wait more than 5 minutes 1/5. Okay, so the probability of waiting no more than 5 minutes for the train is 1/5, or as a percentage, that would be 20%, or you could even write it as a decimal as 0.2. Okay, in problem 3, we're using area to find probability. Okay, so a triangle is inscribed in the square. Point T in the square is selected at random, so somewhere inside the square, I'm going to just close my eyes and put T in there like I'm pinning a tail on a donkey. And what is the probability that T lies in the shaded region? Complete the model below to write an equation. So let's see, we're going to let S be the area of the shaded part, okay? And then the area of the shaded part is the area of the square minus the area of the triangle. So our shaded part is going to be the area of the square, which is 5 squared, minus the area of the triangle. This triangle is 5 for the base, and it's 5 tall, same as the square, so 5 by 5. Okay. Now solve the equation to find the area of the shaded part. So the area of the shaded part is going to be, once again, 5 squared minus 1/2 times 5, which is 25 minus 12.5 for 12.5 inches squared. This is the area of the shaded part. Okay. Number 19, find the probability that the thing will end up in the shaded part. So the shaded part is 12.5, but the whole square is 25. So if we reduce that, we're going to get 1/2. So the probability that T lies in the shaded region is 1/2, or 50%, but if you want to write it as a decimal, you could also put 0.5. Okay, on our last page, we have problem number 4, using area to find a probability. So archery, an archery target has 5 colored scoring zones, so yellow, red, blue, black, white, okay? The radius of the yellow zone in the middle is 12.2 centimeters squared, and the width of each of the other zones is 12.2 centimeters. So if the area hits the target at a random point, what is the probability it hits the yellow zone? Okay, so the radius of the target is 122 divided by 2. That's the whole diameter is 122, which will give us 61 centimeters. Find the probability. So write the probability as a decimal. So we want to know the area of the yellow part, this piece in here, compared to the area of the whole thing. So the area of the yellow part, they told us already, had a radius of 12.2. So we do pi times 12.2 squared. And on the bottom, we're going to do the area of the whole thing, so pi times 61 squared. All right, so 12.2 squared is 148.84, and 61 squared is 3721. Okay, and when I divide that, we're going to get 0.04. So explain why in the calculation pi was not needed to get our estimate. Okay, so we have a pi on the top of the fraction and a pi on the bottom of the fraction. So the pi's will cancel out here. That's why I ignored them when I was writing out the second step. Okay, notice I left off pi there. So the probability that it's going to be in the yellow zone is 0.04, or as a percentage, that's about 4%. Okay, if you wanted to write it as a fraction, it would be, I don't know, 4 over 100, which is 2/50 or 1/25. Okay, so the chance of hitting in the yellow is 1/25 if you pick a random spot there. All right, so as always, pause the video, try your lesson check, and then come back, see how you did, and then decide whether you need to watch the video over again for some more learning. All right, welcome back. In the figure at the right, SQ divided by QT, so this length right here divided by this length right here is supposed to be 1/2. So the blue length divided by the green length gives us 1/2. All right. What is the probability that a point chosen at random, ST, will also lie in QT? So if I choose a random point from S to T, what's the probability it'll hit the green part? Okay. So we're going to do some variables here. So we're going to let SQ equal X. So this length will be X. Then QT is going to be 2X. Remember, we know that this is split evenly. It says 1:2 ratio here. All right. And that means that ST is 3X. So what is the probability of point P being on QT? So the probability of P on QT is going to equal to, let's see, the chance of it being on QT is 2X. The chance of it landing on the whole thing is 3X. So 2X over 3X will give me 2/3. Okay, so there's our probability. Okay. All right, that concludes our lesson for today. Check off the vocabulary words that you understand. So hopefully you know length and area. We've been working with those for quite a long time. And then geometric probability, you might not have done a lot of probability in grade school, the way that you guys skipped around to get here in 8th grade. So just be careful. Remember, it's the things you want over the total things that can happen. So how well can you use geometric probability? If you're not in here, you probably want to go back and rewatch the video. I'll see you in class next time to do some practice, and then we'll get ready for our test.